Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you step on the side, guys, the series that you're following here has to do with graphing quadratic equations. Now, we've been graphing out of Vertex form kind of forever, and we've been talking about transformations with them. I get to still apply stretch factors with a lot of the things I'm going to talk about here. But today I'm going to graph out of what's called factored form, and I'm putting a little spin on it because they're not going to start factored. They're going to start in standard form. For my students, I say let's just keep practicing factoring, and I'll give you a little nugget about what standard form does offer here. It's not the full picture because standard form is really going to be about finding the vertex in a different way. We'll find the vertex using factored form, but one nugget that the standard form thing offers that won't require me to always use my stretch factor if I don't have to. And you'll kind of see what I mean when I choose to use it, and I can actually go back to choose some of those. So I have 12 graphs to do here. They are with this PDF that I have right here in front of me. I'm going to sketch the graph of each function. I'm going to go completely without a table with the exception of when we find the y values for vertexes. And not that I use a table, but I plug the value into my equation to be able to find that y. So here's the general idea, guys. All the equations that you're going to see in front of you are factorable down to a common factor, possibly, times some sort of x minus something, x plus, like some sort of form of just a 1x, not a 2x or anything like that, because I can factor out that too. When we do so, we're going to come up with integer intercepts, x-intercept values. So here's the thing. Y equals x squared plus 4x plus 3 can also be written as y equals x plus 3 times x plus 1. This is the factorization of this. 3 times 1 is 3, 3 plus 1 is 4. Now, why do we do factored form? Because if you want to find x-intercepts, you want to set y equal to 0. The x-axis contains the values of x when y equals 0. Think about it. This is 5, 0, 3, 0, 0, 0, negative 1, 0, negative 6, 0. What do all of these have in common? The y value is 0. And if you want to find the x-intercepts of these, let's set y equal to 0 on this one to find our x-intercepts here. If x plus 3 times x plus 1 equals 0, you use the zero product property and you say either x equals negative 3 or x equals negative 1. These are your x-intercepts. These are the values of x when y equals 0 on our graph at negative 3 and negative 1. These are two of our graph points. They're corresponding, they're at the same height here, as parabolas are symmetrical, and that's the next point that we want to make. This is why x-intercepts are so nice, if it's factorable, if you can find them. Here's why x-intercepts are so nice. Points in a parabola that are the same height are called corresponding points. They're called corresponding because they both reflect. If you reflect across the axis of symmetry in the parabola, you'll land on the other point, which means the axis of symmetry represents a middle value. It represents the midway, the halfway point between these 2 points right here. If I draw a line that looks like this, that goes right down the middle here, guys, this is the line that our vertex is on. The reason x-intercepts are so good to get first is you can find the vertex on this graph by knowing the x value that it lands on. It's on x equals negative 2. Well, what is the vertex itself? It's negative 2 comma something. We need to find the y value still. How are we going to find it? Let's substitute negative 2 into our equation to solve for y. You can either plug it into here, or you can plug it into here. They're both the same exact equation, of course. It doesn't matter. You can do either or. Because I'm going to play with the factored form idea, let's just plug it into this one. So y equals negative 2 plus 3 times negative 2 plus 1. And that's going to be 1 times negative 1, which is negative 1. So the y value of the vertex is negative 2. The vertex is negative 2, negative 1, the y value being negative 1. And we found our vertex point right there. So what did I do so far, guys? I found 3 points on this graph, and the vertex being one of them, which to us is kind of a crucial one, because that shows where the symmetry, of course, is with the graph. And that's where we can now use our stretch factor as we so choose. Now, I didn't write the whole form here for factored form. It would be some sort of a times x minus p times x minus q. I'm not too big on talking about p and q as those letters. They are just they represent the x-intercepts, of course. But I wanted to bring this up to show you that if there's a number multiplied in front of these factors here in a quadratic, that would be your stretch factor. And we can't see a number because it's a 1. That's a 1. The a value being 1 means that our traversal is that of a normal quadratic, where we would go 1, 1, 2, 4. By the way, this all has to do with things that I've done with you guys in the past. And I can also reflect that point across here as well. And that's really the best I can fit. So I think I'm just going to, leave it as that as I now graph the parabola. And I curve her like that. There we go. And there's our beautiful looking parabola. Okay, let's move forward. Let's go to number 2. And let's move me over here. Okay, number 2. Y equals, my phone keeps going off. Give me 1 second here. I'm sorry. Okay, sorry, I'm back. Teachers, man. Teachers talk with each other. And one has to let some things out. Not to me. Or not about me. About their kids. All right. They're students. All right. Number 2. Y equals x squared minus 2x minus 3. Let's, again, the whole goal of this is let's get in factored form. The next video you see from me is likely going to be graphing out a standard form, which has its own kind of benefit ideals. But as long as it's factorable, we can get all these points pretty much in this kind of nice way. So this factors into x minus 3 times x plus 1. Kind of almost close looking to this one, only it's very different as a graph. So the x-intercept here, guys, it's that whole thing where we set y equal to 0, but if you also understand the idea of the x-intercepts are really the reversal of these values, then, I'm kind of good with you really skipping that part. That's the whole goal of factored form, is we know that it's going to be the opposite of whatever these numbers are, but for good reason. It's that zero product property thing. So it's going to cross at 3 for x and negative 1 for x like this. Our axis of symmetry will appear right in between these two values. These 2 points are 4 units away from each other. 1, 2, 3, 4. So if I go 2 away from either point right here or right here, you're going to see that we land on x equals 1. That is our axis of symmetry here. So again, it's always the midpoint, and it's not always going to land on an integer. Okay, that's going to be another important talk that we have to have here, one of the bigger ones. Your main questions will be what happens when we have decimals and fractions and things like that. All right, so the vertex, the x value of the vertex, the axis of symmetry, is at x equals 1. So let's substitute 1 for x, and let's find out what the y value is of the vertex by doing y equals, and we have 1 minus 3 times 1 plus 1. Again, I'm just plugging it into here to solve for the y for the vertex here. This would be the equivalent of me using a table if I had to do this over and over for each number, for each point that we're doing. This is how I'm circumventing the table aspect of it. You still have to find the vertex either way. So negative 4 is the y value. So we're going to get a y value of negative 4 in the vertex. That's 1 comma negative 4. And you know what? Let's just find all of our other points by understanding it's once again a 1x squared and a 1 that goes out there. So this is a 1, 1, 2, 4. Hey, we see that one. 3, 9. And that's all I can fit. And I reflect the point across here. And I reflect this point across here. It's nice to almost get the confirmation that those points fit where they're supposed to, even if you practice that stretch factor thing, you still want to look at that and go like, okay, I landed on a point that I expected to land on there. And that's exactly what happened here. And there's our somewhat U shape. I didn't do it perfectly, but that's okay. All right. And that is number 2. Let's go to number 3. Y equals x squared minus 2x. Now, make no mistake, guys. This is the easiest factoring you can do. Most people get more confused when there are less numbers to deal with. But you factor out an x. You find common factors first, right? That's not going to go. Factor out an x. You get x minus 2. That's it. Now, the x-intercepts. The opposite of the opposite of negative 2 is 2. But what's this one? If this times this equals 0, then either this equals 0. Oh, 0. X equals 0, right? That's another x-intercept. So we get 0 and 2 right here. 0 and 2 is our x-intercepts. Looks like x equals 1 is the midline there. That's the axis of symmetry. Looks like that's a different purple as well. X equals 1. So the 1 is our vertex x value, and the y value will be found by substituting 1 into our equation. So y equals 1 times, looks like 1 minus 1, or 1 minus 2. That's negative 1, which is negative 1 there. So you get a y value of negative 1. So 1 comma negative 1 fits right there. Once again, we know that a value of 1, trust me, you're going to get different a values pretty soon. But an a value of 1 there and a 1 there. So stretch factor of 1, which is 1, 1. How fitting. 2, 4. And again, really all we can fit there. 2, 4. These graphs, we're probably going to see a lot of the same factoring and numbers and stuff like that. It's kind of hard to avoid when you're only working within a confined window and only things that are factorable within said confined window. Because you want to be able to see the whole graph, right? You don't want a graph that goes all the way down here that you can't see it. Okay, number 4, y equals x squared minus x minus 2. Back to a trinomial. Negative 2 times 1 and negative 2 plus 1 would work there. So that's x minus 2 times x plus 1. Okay, so negative 2 and positive 1 are the x-intercepts. Now, here's where things get a little interesting. Suddenly, this axis of symmetry is not on an integer. You can tell these are 1, 2, 3 apart. So 1.5 away would be the axis of symmetry. That's right here. That's at literally negative 1/2. X equals negative 1/2. You could say x equals negative 0.5. I think in some respects, some people are going to kind of want and prefer that. Let's say you didn't, and not that you need a calculator here, but let's say that you didn't have a calculator and this was really something that you had to, oh, you know what? I'm sorry. These aren't even the intercepts, are they? Stop right there. Give me 1 second. I apologize. Everyone's probably drawing this and going, what are you doing, Mr. Robinson? The x-intercepts are x equals 2 and x equals negative 1. Let me just take my software and yoink. I really wanted to talk about the axis of symmetry being a decimal, that I just screwed that up. I'm sorry. There we go. X doesn't equal negative 1/2. X equals positive 1/2. How did I even catch that? That was my mistake. I don't know. But x equals positive 1/2 here. So let's talk about that again. It's still a half. Let's say you didn't have a calculator, and let's say that there's something where you didn't know how to work with the decimals in calculation. Could you conceivably work with a 1/2 in here? 1/2 minus 2 and 1/2 plus 1. And don't do a mixed number because you got to multiply here. That's 1/2 minus 4 over 2 times, a lot of people just want to use the decimal. I know, especially for halves. Next time I'll use the decimal for this one. 1/2 plus 2 over 2, common denominator. And that's negative 3/2 times positive 3/2, which is negative 9/4. And this is probably an instance where you're like, well, maybe we should have used the decimal in calculator, Mr. Robinson. I don't know what negative 9/4 is as a decimal. It's negative 2 1/4. So negative 1, negative 2 1/4. It's going to be right there. Now, no matter what, you'd get negative 2.25. You're still going to have to work with the decimal thing. That's the point. It gets a little tough. Now, the other little tough part about this, if you think about it, guys, is although our stretch factor is 1, which is beautiful, we still would have to do that 1, 1, 2, 4 stuff, and we're not exactly on the crosshairs of these grid line, markings here. If I do 1, 1, it's like 1, 1, like that, and then reflect that point across like that, and like 2, 4. These aren't really the most desirable kinds of points that we wanted out of this thing. And you can plot them. I'm not stopping you from plotting them. But, there are other points that actually do land on integers here that we would be able to find. And this is, I think, where it's going to be a nice time for me to talk about the y-intercept. The benefit that standard form actually gives us. And this will be a heavier topic of conversation when we're actually doing standard form. But I think now's the time I want to bring it up. All of these equations are in standard form before I factored. All of these ones right here. In standard form, of course, guys, was y equals ax squared plus bx plus c. Well, as I mentioned from x-intercepts, guys, x-intercepts are the values of x when y equals 0. Y-intercepts are the values of y when x equals 0. So the y-intercept, if you turn x into 0 here, you get 0 plus 0 plus c. The y-intercept of all our graphs appears at 0, comma, c. The constant in your standard form equation is the y-intercept. Don't believe me? Look at number 1. You see that 3? There it is. Look at number 2. You see that negative 3? There it is. Number 3. You see that 0? There it is. And number 4. You see that negative 2? You want to know where this thing crosses? Right there. Right there. That negative 2. That's right on that integer value. So as I kind of undo some of those, we hit right here. This y-intercept, this is a point. And here on out, I'm going to plot the y-intercept immediately. I'll just go ahead and plot it and say, that's a point. We can use it. Just confirm it with the rest. That's a point. And you know what else is really good about that? Is there's also a corresponding point we can find right there. Now, it's going to be hard for us to kind of find other things here. I can't count here and say like 1, 1, 2, 4. But those are other solid points that we know that it goes through. And of course, this is right next to it. Others won't be quite as right next to it, and I think we'll be a little better off. I don't know if I can really find another really good point for you, though, beyond that. Let's just see if there's a 3, 9 that kind of exists here. 1, 2, 3, 2, 3, 4, 5, 6, 7, 8. Oh, it's kind of above the graph. So it does reach kind of in this area right there, though. So there's an idea of this part of the curve, just so I can give it to you. But that is, what we're playing with on that part right there. And that's our parabola. Not quite as easy as the other ones, but listen, we don't really have an option. There's not really much else we can do. The vertex is the fraction. Consider if you got this into vertex form. Getting this into vertex form would mean the whole completing the square process, dividing this by 2 and squaring it. So dividing an odd number by 2 means you're going to be left with some fraction in some capacity anyway. And that's just the nature of what you're going to have. There's no way around it. Okay, number 5, guys. Number 5 is our first problem where besides just factoring the quadratic, we're also, well, I take it back. Number 3 had a common factor as well. But I want to get the common factor portion before we factor the trinomial. So on number 5, let's factor out a negative, and we're going to get x squared minus 4x plus 3. And now we factor this part down here. That is x minus 3 times x minus 1. Now there's a negative on the outside that won't affect our intercepts, but that is for your a value. All right, so a in this problem is negative 1. Not our axis of symmetry, but the a value. The x-intercepts are at 3 and 1. I don't know what I was pointing at here. But they're at 3 and 1, so we're going to start right there. I'm going to go ahead and draw my axis of symmetry down the middle of those two, on the 2. And the vertex is, oh, by the way, negative 3 is the y-intercept. And now that I have the axis of symmetry, here's another point that corresponds over here. So I have 4 points of this thing. I just need the 5th one. If you know parabolas well enough, you probably know where it is. I'll give you a hint. It's not right here. It's not a V shape. It's not right there. All right, the vertex is at 2 comma what? Let's plug this in for y. We're going to get y equals, and I'm going to go ahead and use the factor form again, negative 2 minus 3 times 2 minus 1. And we get y equals negative, the opposite of negative 1 times positive 1, which is a positive 1 right there. Have you guys noticed that every time I'm doing the vertex thing, these two numbers are always opposite of each other? Negative 1 times 1, negative 3 halves times 3 halves, 1 times negative 1, 1 times negative 1, and negative 2 times 2. Have you noticed those are always opposites when I'm trying to find the vertex value of that? Did you know that that'll always be true for finding a vertex when you're plugging in the x value? Yeah, it'll always be true. And standard form also has a little nifty thing as well when you're plugging in the x value to find the vertex. It's kind of the same thing, but not really. I'll show you when we actually do standard form out of it and we're plugging in the x value. All right, there's our graph though, guys. That was 2 comma 1. There's the vertex. I already had another set of 1, 1, 2, 4, and remember it's an a of negative 1. It should be doing that, going down that amount. So I got 5 points. We're all good to go. And you can see where we get to go a little faster per problem, assuming there's nothing to, oh my gosh, we got some things here. All right, number 6, y equals 1/2 x squared plus 3 halves x minus 2. Now, a couple of things. First, let me move my face. Second of all, let's plot the y-intercept of negative 2. Let me do that before I forget. The y-intercept is negative 2. All right, that's a nice point we can have. But I'm still going to factor this. And I want to factor it in such a way, guys. I really want to still get out that common factor. And, I just want to get that 1/2 out of the way. I already have another fraction here, and, if I can get rid of it, that'd be awesome. So I'm going to turn into y equals 1/2 times, and, when you factor a 1/2 out, everything inside is doubled, because taking half of those things would get back to where we were. So 1/2 of what is 1/2 x squared? Well, x squared. If I take half of something to get 3 halves, that something was 3, right? 1/2 times 3 is 3 halves, so that's going to be a 3x, and half of -4 is -2. So this is x squared plus 3x minus 4. So this is y equals 1/2 times x plus 4 times x minus 1. Okay, lots to unpack with this one, guys. We have the 1/2 stretch factor, A. A is 1/2 stretch factor. We have what looks like a x-intercept. X-intercepts of -4 and 1. The opposites, right? -4 and 1. Which means, looks like we're going to get another axis of symmetry that's on a fraction again, on one of those 1/2s. I think I promised this time I would do a decimals instead, and call it -1.5 for you. I can see why it can be more beneficial based on what you're doing here, assuming you know something about the calculations with it. If you don't have a calculator, though, I don't know. So the vertex, the x value is at I'll say at 1.5. I'm more inclined to say that for a word problem, though, depending on what we're doing. I don't want to do an improper fraction for a word problem. All right, so -1.5. Let's go ahead and plug those into here. Now that's y equals 1/2, which is a fraction. Half of -1.5 plus 4 times -1.5, 5 minus 1. So let's do half of 2.5 times -2.5. You see how they're opposites again? That's half of -6.25. Oh, that's -3.125. All right. -3.125. 0.125 is 1/8. So this is -3 1/8. Once again, it's really close, to this thing right here, even closer than a quarter would be. So about like that, as this thing really stretches out. Oh, -3. I was going to say, geez, that's not quite right. Okay, right there. I'm sorry about that. As it stretches out kind of fast to get to that part right there. By the way, there's a reflective point that's 1.5 away over here. You know what? That's 5 points in and of itself. It's kind of hard to get other ones, given that we're at the fraction that we're at. But if there's one that I could do, could I fit 4 over? If I went 4 over, 1, 2, 3, 4, normally we'd go up 16, but because A is 1/2, we'll go up half of 16, which is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll get this point right here with that -1/8 kind of height thing. Not -1/8, but you know what I mean. An 1/8 away from that thing, and I think over here as well. Okay, so there we go. I like evening out with a parabola a little more with any point that I can fit that far out. Totally excited about that. All right, so that's the first 6 problems there, and I think you've hit most of the ideas of what can be a little interesting on these problems. You're going to deal with some more decimals and stuff like that, but I think we've kind of gotten the extent of what they are. But all these will now kind of have some form of common factor. Okay, not that anything might be a little too alarming. And, the less fractions, the better, I guess. All right, so number 7. Factor out the negative. So -x squared minus 2x minus 3. And now the inside there, that's x minus 3 times x plus 1. I don't know why that took so long. X minus 3 times x plus 1. Again, only so many different ways we can do this. Oh, by the way, the y-intercept will be 3. It's based on the original standard form, right? The y-intercept of this thing will be 3. X minus 3 times x plus 1. The x-intercepts. Let's see if we can do this without me labeling all that. The x-intercepts are going to be 3 and -1. And this makes sense. Looks like the only way to make this graph the way it is if it's upside down, and it makes sense to be upside down because it's a negative. So the axis of symmetry is at x equals 1 here. That's halfway between 1 and 3. Let's try, and again, I'm going to try and do this a little more on a less righty scale and more just graphy. Let's see if we can plug that in. 1 minus, I don't know. I can do it, but hopefully you can follow along. 1 minus 3 is negative 2. 1 plus 1 is 2. We're going to take the opposite of negative 2 times 2. So we're going to get 4. So our vertex is at 1 comma 4, like that. 1 comma 4. There we go. And of course, the reflective point with the y-axis, boom, is like that. And there's our 1, 1, 2, 4, hey, 3, 9. And reflect that point across as well. And there is our graph. So vertex form takes a little bit, well, remember, this I had to factor this first. Vertex form takes a hair of work to find the vertex. You're going to have to use the same hair of work to find it out of standard form. Or you can, of course, get it into vertex form if you're in standard form. But, of course, also takes a hair of effort. No matter what you do, it's going to take a little bit of effort. At least in factored form, you get 2 quick points easily. It builds your axis of symmetry so you can reflect across the... It just kind of works kind of nicely that way. All right. Number 8. There's a negative 2 that can factor out of this one. So this will be y equals negative 2 times x squared plus 4x plus 3. Again, not very new as far as the intercepts goes. I hope that's okay. This is x plus 3 times x plus 1. So your x-intercepts are negative 3 and negative 1. Maybe that is the first time we've seen that one. By the way, your y-intercept is negative 6 all the way down here. Okay. The axis of symmetry is at negative 2. Goes right through right there. And if that's the axis of symmetry, then we have a corresponding point that's 2 away over here. We're getting our points in. And the vertex, we can find the vertex now. If x is negative 2, let's plug it into this equation. That's, I'll write this one in for the y value here. We're going to get negative 2 plus 3 times negative 2 plus 1. Once again, those look like opposite numbers. That's 1 times negative 1 times negative 2. So negative 1 times negative 2 is positive 2. So your vertex is at negative 2, positive 2. Negative 2 for x, positive 2 for y. It's right there. Does this follow along with the idea that a is negative 2? Here we go. Instead of 1, 1, we're going to go 1, 2, double that height. Instead of 2, 4, we're going to go 2, 8, double that height. And of course, they go downward. So there it is. We got our points there. We're all good to go. Not bad, folks. 4 more problems. All right, number 9. Y equals 2x squared minus 4x. Once again, try and get a common factor here that you can. I can factor out a 2 and an x, and I'm going to be left with x minus 2. Now, as far as factors go, let me wrap that around parentheses so you can really see that this is the a value, of course. And then we have x-intercepts of, remember, this one is an x-intercept of 0. You can think of it as x minus 0, you know? But it is an x-intercept of 0, and then this x-intercept of 2. So, I'm going to be in the way here. So it kind of looks like that one that we had before, only it looks like now with a stretch factor of 2, things change slightly. And by the way, the y-intercept is also 0, you know? 0 as that was 0, and there's really no way around that. So x-intercepts are 0 and 2. The vertex, the halfway point in between those two, is x equals 1. Let's substitute 1 into our equation. And we'll get y equals 2 times 1 vertex. 2 times 1 times apparently negative 1. 1 minus 2. So 2 times negative 1 is negative 2. So your vertex is at, negative 2. So your vertex is at 1 comma negative 2 right there. Right there. Now, I only have 3 points so far. The y-intercept was the same as the x-intercept, so I have to find more points. Let's use that stretch factor of 2. 1, 2, 2, 8. If you've been with me for a while, you know what I'm talking about with these, given that these are quadratic equations. Doubling the 4 being 2 squared. All right. Oh, no. Oh, no. Not bad. Actually, that's pretty good. Okay. Now check this one out. y-intercept of 30. Now, I can't fit that y-intercept on this graph. That just means that, as it passes somewhere, it's going to go like, whoa, super tall. It won't hit the y-intercept there. So we're going to have to, manufacture these on our own as we go forward. So let's go ahead and factor, though. Got a 2 that can pull out. Okay, x squared plus 8x plus 15. Oh, I know what that factors to. That is x plus 3 times x plus 5. So our x-intercepts are at -5 and -3. -3, -5. So -3, -5. The vertex is at x equals -4. Halfway in between. Now you might know where this goes based on distance stuff. I mean, I don't know. How much should I do the math versus show you methods that you want to consider once you understand these graphs more? Do you understand that when these two are each 1 away from here, and the 2 is the whole 1, 2 kind of thing, and it's positive going upward, that we have to be 1, 2, 1, 2? Do you know that it's going to be right there? I'll still do it. But, that's one of those things where can you save time? Where have you seen this graph before? Where can you understand it? Because the a value is 2, they would have to be there. Anyway, so let's see if that works. -4 plus 3 is -1. -4 plus 5 is 1. 2 times 1, -1 times 1 is -2. So -4, -2 is the vertex right there. And again, we don't get the y-intercept value, so we're going to have to keep going. Let's get, that was 1, 2. How about 2, 8? Like that right there, 2, 8. And that is our parabola right there. Maybe a little too curvy, that's okay. All right, 2 more. 11 and 12, here we go. Let's factor, we got to factor 1/2 out of both. It's not a problem. It's actually probably easier. You get to double the values instead of divide by 2. So on number 11, let's factor the 1/2 out. Let's try that again. Let's factor the 1/2 out. We'll get x squared plus 5x plus 4. Right? We double everything inside there for the half. And that factors at x plus 4 times x plus 1. So the x-intercepts are -4 and -1. So welcome to another fraction, if you will. By the way, y-intercept of 2, that's another point right there. Now the axis of symmetry is going to be halfway in between -4 and -1. That's at -2.5 right here. This does help us, remember, get the corresponding point across where the y-intercept was. So y-intercept is 1, 2.5 away. So this is half, 1.5, 2.5 away. There's another point. Getting some good points here. This one is harder to predict where this vertex is. Even I couldn't tell you right off the bat. So let's go and figure that thing out. If this is x equals -2.5, and I will uphold my bargain of using the decimal, even though I shouldn't. The vertex y value is y equals 1/2 times, and once again there's that 1/2, -2.5 plus 4 times -2.5 plus 1. So that is half of positive 1.5, and of course what probably should be -1.5, it is. So that's -2.25, and half of -2.25 is -1.125. Okay, so that's -1 and an eighth. -1 and an eighth, so about right there-ish. And again, that's enough points for me there. If you did a 1-1, well then, you're right there. I mean, you're getting close to hitting that stuff anyway. So there's what can be our parabola here. I just realized I got to graph these from the top. Doesn't look like I'm really good at doing them from the bottom. It probably does hit that next set of points over, but that's okay. All right, last one. Number 12. Let's go ahead and factor out that 1/2 again. So we'll get y equals 1/2 times x squared plus 8x plus 12. because we're doubling everything that's inside, because taking half of those would take half of them. 12 is too high when it comes to a y-intercept, so let's just keep factoring that thing down. That's 1/2 times x plus 6 times x plus 2. So we do get intercepts of -6 and -2 for x-intercepts. I just put x equals. I hope that's okay. -6 way over here. -2 is way over here. All right. 1/2 is the stretch factor. Keep that in mind when we're figuring things out. -4 is exactly halfway in between these. So right there. That's the x value for the vertex. The y value, let's go ahead and try that. The y value is going to be 1/2 times -4 plus 6 times -4 plus 2, which is half of +2 times -2, which is -2. -2 divided by 4 is -4 divided by 2 is -2. So -2 right there. So that'll be at -4 and -2. There's our vertex. So let's see if this makes sense with what, as I'm going to kind of work out a stretch factor thing as I graph this. So this is, instead of 1, 1, we're going to go 1, 1/2. Oh, you know what? I messed up with the 1, 1 thing here when I went up here. That obviously wouldn't have hit. This would have gone 1, 1/2. That's my bad. I was looking at that and going, I might have graphed something wrong, but there we go. So 1, 1/2. Instead of 2, 4, it's 2, 2. Instead of 3, 9, it's 3, 4.5. Instead of 4, 16, it's 4, 8. Oh, you know what? The 12, I'm sorry. Did I say 12? I'm sorry. It's the 6. The 6 is the y-intercept right here. My bad. There it is. So that's 6. But, you know, I can't reflect this other piece right here. I can't even reflect this one here. So I can reflect this one. So, sorry. Best I can do there is do that. It's not going to be the perfect symmetry that I want. Yes, it goes forever in this direction. But I get to show a little more of it right here. And we get that point going right there. All right, and yeah, I could extend it, but it's going off the screen. You know what? That looks weird if not. Let's extend it off the screen. That looks much better. Okay, guys. All right, guys, so that'll do it for this one here. So this was me graphing out a factored form. I factored it first. Generally, they would give it to you in factored form. That's its advantage, I suppose. Although in standard form, when it's factorable, we do get this. We get almost 4. We get at least 3 points out of just using factored form. Getting the 2x intercepts, of course, but then also getting the vertex based on those intercepts. Now, you're going to find a way to get a vertex through standard form that's probably equally as quick, probably a hair quicker. But you still got to plug the value in, and standard form gave us that intercept thing, which I'll talk about more in the future. So that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.